All right, let's just jump right in. When you hear the word symmetry, you probably think of something like a butterfly's wings, right? Or maybe a perfectly designed building. It's familiar, it makes sense. But what if I told you that our entire reality is being shaped by a much, much deeper, totally invisible kind of symmetry? A kind of symmetry so powerful, it's literally forcing physicists to go back and rewrite the entire rulebook of the universe. Yeah, it turns out that what we normally think of as symmetry, that's just the first page of a much bigger, much stranger story. We're about to dive into this new kind of order in the universe, one that's not about breaking symmetry, which is the old way of thinking. No, this is about symmetry acting as a protector. Okay, so before we can really get into this wild new idea, we've got to make sure we're all on the same page. We need to understand what symmetry really means to a physicist, because it's a concept that goes way beyond just pretty patterns. It scales all the way up to the fabric of the cosmos itself. So, in our everyday world, symmetry is all about shape. You can take a butterfly, flip it, and its wings match up perfectly. Or rotate a snowflake, and it looks exactly the same. That's what scientists call invariance under a transformation. It's a fancy way of saying it stays the same even when you do something to it. But here's where it gets really interesting. Physicists take that simple idea and they run with it. For them, the ultimate symmetry is that the laws of nature, the fundamental rules of the universe, are the same everywhere. The law of gravity works here on Earth, just like it does in a galaxy billions of light years away. The rules of physics don't care if you run an experiment today or 1,000 years from now. Now that is a deep, profound, universe-spanning kind of symmetry. And get this, the brilliant mathematician Emmy Noether figured out something incredible. She proved that for every one of these deep symmetries, there's a physical quantity that has to be conserved. It's a one-to-one link. So the laws of physics are the same everywhere in space? Boom. That's why momentum is conserved. The laws are the same at all times? Bam. That's why energy is conserved. So the takeaway here is huge. Symmetry isn't just about things looking nice. It's the fundamental reason our universe has stable, predictable rules at all. Okay, so for decades, physicists had this really solid, really successful theory about how different states of matter work. How you get ice, water, steam, and the whole thing was built on the idea of symmetry. But then they started looking at the quantum world, and they found something that just broke all the rules. So the big idea at the time, called Landau theory, said that phases of matter are all about breaking symmetry. Think about it. You have chaotic, messy water molecules, and when they freeze, they snap into a highly ordered, very symmetrical ice crystal. They break their random symmetry to form a new ordered one. Made sense. But then 1982 rolls around, and scientists discover something called the fractional quantum Hall effect. It was this bizarre, completely new state of matter that just didn't fit the theory at all. It forced them to come up with a whole new idea, something they called topological order. So here's the best way to think about the difference. The old rule, symmetry breaking, is kind of like balancing a pencil perfectly on its sharp tip. Right at that moment, it has perfect rotational symmetry. You can spin it and it looks the same. But it's super unstable, right? The slightest breeze and it falls over. It breaks its symmetry to find a more stable state, lying on its side. But this new puzzle, this topological order, was the exact opposite. These were states of matter that were weirdly, mysteriously robust. You could poke them, you could nudge them, and their special quantum properties didn't care. They just stayed. And the old theory had absolutely no explanation for that kind of stability. And the solution to this puzzle? Well, it was a total game changer, a complete paradigm shift. It was this idea. What if symmetry wasn't the fragile thing that gets broken? What if symmetry was the protector? And that gave birth to this amazing concept, a symmetry-protected topological phase, or SPT for short. And it's exactly what it sounds like. In these materials, symmetry acts like a bodyguard for all the cool, exotic quantum properties. These special properties don't just exist alongside the symmetry. They exist because of it. So if you could somehow find a way to break that underlying symmetry, poof, the special quantum stuff would just vanish. It's a complete 180 from the old way of thinking. And one of the craziest things that comes out of this is that these protected states can exist in more than one lowest energy setup at the same time. Physicists call them degenerate ground states. Now, normally, any tiny little disturbance would make a system just pick one configuration and stick with it. But not here. That bodyguard, the protecting symmetry, makes all of these different states incredibly stable and robust. So you're probably wondering, how on
earth do physicists find these things? Well, they use some really, really powerful and abstract math. You don't need to remember the name group cohomology. But here's what it does, which is so cool. It basically acts like a special detector. This math can tell physicists with complete certainty whether a specific kind of symmetry is the right kind to create one of these super stable protected states. It's like having a mathematical treasure map that leads directly to brand new forms of matter. Now, this whole new way of thinking about symmetry, it's not just a one-trick pony that explains one weird effect. No way. It's turned into a powerful new toolkit that physicists are now using to crack other really tough problems in the quantum world. And a perfect example of this is a concept called supersymmetry, or SUSY for short. It's this beautiful, elegant idea that proposes a hidden symmetry between the two basic kinds of particles in the universe. You've got the particles that make up stuff, called fermions, and the particles that carry forces, called bosons. SUSY says they're partners. And by mathematically pairing them up like that, you suddenly get these amazing shortcuts to solving problems that were once ridiculously complex. And this toolkit is seriously useful. It gives you a much, much easier way to solve the classic hydrogen atom problem, something that every physics student has lost sleep over. It helps improve other methods for getting approximate answers, and it even pops up in fields like statistical mechanics. It just goes to show you, when you think about something as fundamental as symmetry in a new way, you can unlock progress all across physics. Okay, I get it. I know what you might be thinking right about now. Group cohomology? Partner Hamiltonians? This all sounds super abstract, right? Like, why should anyone who isn't a theoretical physicist even care? Well, there's a quote from one of the papers we looked at for this that just nails it. The history of science is absolutely full of examples of this kind of pure what-if research that seemed totally useless at the time, but then later became the bedrock for technologies that changed the world. Think about it. Electricity, Einstein's relativity, quantum mechanics itself. They all started out as weird, abstract ideas. And you can see the path laid out right in front of us. It starts with this really abstract math about symmetry. That math allows you to predict these wild new states of matter, these SPT phases. Then, experimentalists can go into the lab and try to actually create materials that have these amazing symmetry-protected properties. And the final step? What do you build with them? Well, these incredibly stable quantum states are the absolute perfect ingredients for building something called a topological quantum computer. And that's a revolutionary new kind of machine that could solve problems that are literally impossible for even the most powerful supercomputers we have today. So you see, by digging deeper into an idea that seems as simple and basic as symmetry, we're not just solving some old, dusty physics puzzles. We're actually discovering a whole new language to describe reality itself. A language that's pointing the way to technologies we can barely even dream of right now. And it really makes you wonder, doesn't it? What other huge secrets about our universe are just sitting there, waiting for us to unlock them, with the next big idea about symmetry?